Hello. Okay, so the following video is a theoretical derivation of the formula that you will be using. Now, this is not in the higher course. You do not need to know this derivation. Okay, so you can completely skip this video if you want to, but I am making it just for completionist sake, and for those of you that might be interested in it. You can ask me questions on this, and as I said, you do not need to know this for higher. You only need to know the equations that it actually comes out with at the end. So I will tell you the equations when we get there. So this video is going to be a standalone on its own, just for the proof of the formula, and then I'll make another video just using the formula. Okay, so we're considering two parallel rays of light entering an optically more dense medium. Okay, so V1 is the speed they're going in medium 1, and then they're going into a more dense medium V2 with that speed V2. Okay, so medium 2 is optically more dense than medium 1 because we've just been told that. So therefore, the second speed is going to be less than the first speed. If you think about it, your speed in air is a lot quicker than your speed through water. Okay, similar kind of thing like that. So I've done the next couple of bits already. So insert angle θ1, so with the angle of incidence in medium 1 into 3 places in the diagram. So the two obvious ones are this one and this one, okay, because they're just the angle of incidence. Now, to find the last one, I've said that here there's a 90-degree angle there. So this angle here would be 90 minus θ1. There's also a 90-degree angle there. So if that is 90 minus θ1, then this one has to be θ1. Okay, and similarly, I've applied that same kind of thing for θ2. So θ2 is the angle of incidence in medium 2, or the angle of refraction in medium 2. So the two obvious ones between the normal and the ray. And then again, if we use some 90-degree geometry to say that this part here is 90 degrees to there. So this is 90 minus θ2. So, and this is also 90 degrees. So that must be θ2. Okay, so suppose that in time t, so little t, the light travels at speed 1 meters per second from B to C. So B to C is there. Then also in time t, the same time, so time t, the light travels at V2 from A to D. So it's just that part there that's moved into V2 while this is still traveling from B to C. So from A to D. So, but also distance is speed times time. So that distance BC is the speed V1 times by time. And it says rearrange this to make the speed the term of the subject. So V1, so speed is distance divided by time, so VC divided by T. Okay, so nothing too difficult just yet. So in medium 2, again, distance is speed times time. So in medium 2, we've got that A to D is the distance, and speed is V2 times by the same time. Rearranging that to make the speed the term of the subject, V2 is distance divided by time. Okay, so we've got two equations there. We've got equation 1 and equation 2. So the next part is dividing equation 1 by equation 2. So V1 divided by V2 is BC over T divided by AD over T. And we know that if you divide something, you can times it by the flipped version of it. So we end up with having V1 over V2 is BC over AD because those T's cancel out. Okay, so now it says, now identify using the letters on the diagram two right-angled triangles which share a common hypotenuse. So if we go back up to this diagram here, okay, so I'm going to use this multicolored pen. We've got two right-angled triangles that share a common hypotenuse there. Okay, so I'm going to redraw that just nearer to where we're working, just because it's easier to refer to when I'm drawing it. So we've got sort of right angle triangle, which is ABC, and that's θ1. And we've also got a right angle triangle there, and that's D. And that angle there is theta 2. So triangle 1 is ABC, and triangle 2 is ADC. By that I just mean ABC. That's one triangle. And ADC is another triangle. Right, using trigonometry on the right hand triangles. So sine theta is opposite over hypotenuse. That kind of trigonometry. So sine theta 1 is opposite, so BC over hypotenuse over AC. And sine theta 2 is opposite, so AD over the hypotenuse over AC. And then it asks us to divide the first equation by the second equation. So sine theta 1 over sine theta 2. Oh, it's looking a little bit familiar now, isn't it? Sine theta 1 over sine theta 2 is BC over AC divided by AD over AC. So again, we can times it by the flipped version of it. So get rid of the ACs. So it's BC over AD. We also know from previous refraction experiments that N2 over N1 is sine theta 1 over sine theta 2. So hence, N2 over N1 is BC over AD because it's sine theta 1 over sine theta 2. Okay, now equation 3, back up to equation 3 here. We also know that something else is BC over AD, it's V1 over V2. So using the information from equation 3, we now know that N2 over N1 is BC over AD, which is V1 over V2. Which we also know now is sine theta 1 over sine theta 2. So the refractive index is the ratio of the speeds of the light in the two media. So N2 over N1, we know is sine theta 1 over sine theta 2 because we did that in the earlier lesson. But now we also know that N2 over N1 is equal to V1 over V2. And also, because V1 equals the frequency times the wavelength 1, remember the frequency doesn't change, and V2 is the frequency times wavelength 2, then we can use basically V equals F lambda to say that N2 over N1 we know is V1 over V2, but it's also F lambda 1 over F lambda 2. That frequency can cancel out because that doesn't change, so N2 over N1 is equal to wavelength in medium 1 divided by wavelength in medium 2. So the refractive index is also the ratio of the wavelength of the light in the two medium. Okay, so as I said, you don't need to know this at all, but it's just for information. What you really need to know is the summary at the bottom. So I'm going to stop the video now, and then we're going to talk through the summary for those of you who didn't want to watch the explanation of where we get these